Graphs of rational functions. Rational functions can be written as fractions, or functions that can be written as fractions. For this section, our rational functions will be a polynomial over a polynomial. It's pretty involved to draw the graphs for these. So we're going to take each little step separately and practice them separately, and then at the end we're going to put it all together to draw the entire graph. So let's start with x-intercepts, and x-intercept is the value where the graph crosses the x-axis. In other words, it's the x value when y equals 0. To find it algebraically, set the top of your fraction, the numerator, equal to 0. So x minus 5 equals 0, and solve that, add 5 to both sides, x equals 5. So our x-intercept is at 5. What that looks like on the graph is you go to 5 on the x-axis and just put a dot. Let's do another x-intercept for g of x equals 10x plus 2x plus 10 over x plus 1. So to find the x-intercept, you set the top equal to 0 and solve. Subtract 10 from both sides and divide by 2. So x equals negative 5. On the x-axis, we go to where x equals negative 5 and put a dot. That's the x-intercept. Now let's practice the y-intercept. The y-intercept is where the graph crosses the y-axis. So it's the y value when x equals 0. To find the y-intercept, replace all x's in the function with zeros and simplify. And I'm going to write a y instead of f of x, so y equals, and replacing all of the x's with zeros would give us a negative 5 on top, a 3 on the bottom, negative 5/3, which is negative 1 2/3. So the y-intercept is on the y-axis. I would go down 1 2/3, about right there, and put a dot. Trying it again, f of x equals 3x over x plus 2. So y equals, replace all of the x's with zeros, and we have 0 over 2, which is just 0. So where y is 0 is right here on the origin. So that's x-intercepts and y-intercepts. Now we know that you cannot divide by 0. So any fraction that we have, we're not allowed to have a 0 in the bottom, but there are some values of x that would cause this to happen. So to figure out what would cause a division by 0, set the bottom equal to 0. So x minus 2 equals 0, x equals 2. If x was 2, we would have 3 divided by 0, which is not allowed. So on our graph, we mark off a boundary where x is 2 with a straight up and down dotted line. And that tells us our graph is not allowed to touch that dotted line, because that would mean x was 2, which would mean we're dividing by 0, not allowed. That straight up and down dotted line is called a vertical asymptote. It marks off places where the graph is undefined. Trying to have a negative under a square root would cause the same sort of problem. But for what we're doing, it's just if the bottom of our fraction equals 0. So figure out what would make the bottom be 0 and put a vertical dotted line on that place on the grid. When you have an x squared on the bottom, you need to factor first. So this one would be 5 over, and we have a difference of squares. The square root of x squared is x. Square root of 16 is 4. So that factors into x minus 4, x plus 4. Now to find our vertical asymptotes, we're going to set both of those parentheses equal to 0. X minus 4 equals 0, x plus 4 equals 0. And solving, x equals positive 4, x equals negative 4. So this function has two vertical asymptotes, one at positive 4, so put a dotted line on positive 4 and one at negative 4. So the graph is not allowed to touch either of those dotted lines. It will get very close to it, but it can't cross it or touch it. This function also must be factored. So if I look at negative 8 and try to figure out the factors of negative 8 that I can add to get negative 2, we would have a negative 4 and a positive 2. So negative 3 over x minus 4, x plus 2. Now, for the vertical asymptotes, we're going to set those both equal to 0. X minus 4 equals 0, x plus 2 equals 0, and solve. So our vertical asymptotes are at x equals 4 and at x equals negative 2. So dotted line at negative 2 and a dotted line at positive 4. So we've done x-intercepts, y-intercepts, vertical asymptotes. Horizontal asymptotes. To locate these, we need to define some terms and then look at a set of rules. So the terms we need to understand are degree and leading coefficient. Degree is the largest exponent of a polynomial. Leading coefficient, which we'll just call LC from now on to save room, the number in front of the letter with the biggest exponent. So for example, if we're looking at f of x equals 5x squared minus 7x cubed plus 3x plus 1, the degree, the largest exponent, is 3. And then when we look at the number in front of the x cubed, negative 7, that's the leading coefficient. So we'll need both of those terms with our horizontal asymptote rules. There are 3 different scenarios for horizontal asymptotes. We're going to let A be the degree of the numerator, or the top, and B be the degree of the denominator, or the bottom. The first scenario would be if A is greater than B. If this happens, there is no horizontal asymptote. So looking at this example, the degree of the top, which we'll represent with A, the biggest exponent is 3. On the bottom, the biggest exponent is 2. So A is greater than B, therefore there is no horizontal asymptote. The second situation would be if A is less than B. When that happens, the horizontal asymptote is y equals 0, which is the x-axis. So looking at f of x equals 1 over x, the degree of the top, there's no variables at all on the top. Wait, I didn't mean to do that. There are no variables at all on the top, therefore A is 0. The degree is 0. On the bottom, the biggest exponent is 1. A is less than B, therefore the horizontal asymptote is y equals 0. And that is just the x-axis. So there's our horizontal asymptote. Usually graphs do not cross horizontal asymptotes, but once in a while they do towards the middle. The final situation would be if A equals B. Then the horizontal asymptote is y equals the leading coefficient of the top over the leading coefficient of the bottom. So in this example, the degree of the top is 2. The degree of the bottom is also 2. So leading coefficient of the top is 2, leading coefficient of the bottom is 3. Our horizontal asymptote is y equals 2/3. So we go up to where y is 2/3, about right there. And there's our horizontal asymptote. more practice finding all the vertical and horizontal asymptotes. First example, g of x equals 7x minus 2 over x minus 3. Vertical asymptote, you set the bottom equal to 0. So x minus 3 equals 0, x is 3. Horizontal asymptote, we have to follow the rules. The degree of the top is 1. Degree of the bottom is also 1. So the horizontal asymptote is leading coefficient over leading coefficient. Y equals 7 over 1, or just 7. For the next example, t of x equals 3x plus 4 over x squared minus 49. If there's a squared on the bottom, you need to factor it first. Again, we have a difference of squares. That would factor into x plus 7, x minus 7. Vertical asymptote, set the bottom equal to 0. So x plus 7 equals 0, x minus 7 equals 0. X is negative 7, x is positive 7. We have two vertical asymptotes. To do the horizontal, go back to the unfactored form so that you get the degrees correct. The degree of the top would be 1, the degree of the bottom would be 2. A is less than B, so when that happens, the horizontal asymptote is y equals 0. Q of x equals x cubed minus 1 over x plus 1. Vertical asymptote, x bottom equal to 0, x plus 1 equals 0, x equals negative 1. Horizontal, the degree of the top is 3. Degree of the bottom is 1. When A is greater than B, horizontal asymptote, none. And then one more, and then we're going to put it all together. Now, the bottom is already factored. We're not going to worry about factoring the top on these particular problems, but the bottom is already factored. So for the vertical asymptote, I'm going to set each factor equal to 0. 7x equals 0, x minus 4 equals 0. And divide, x is 0, x is positive 4. But to do horizontal, we need the unfactored form. So let's multiply that back together. That would be 7x squared minus 28x. That way we'll get the degree correct. The degree of the top is 2. The degree of the bottom is also 2. So the horizontal asymptote is y equals leading coefficient over leading coefficient. Now, let's put all of the things together and draw a complete graph. This is the plan we're going to use. Your book might have something a little bit different, but I would like you to follow these exact steps. First, completely by hand, we're going to do these first steps, everything we just went over. The x-intercept, set the top equal to 0, draw that point on the x-axis. Y-intercept, replace all x's with zeros, draw the y-intercept on the y-axis. The vertical asymptotes, set the bottom equal to 0, draw your up and down dotted line, maybe 2 of them. Horizontal asymptote, follow the rules according to the degree of the top and the degree of the bottom, and draw a horizontal dotted line. So by hand, you're going to draw all of those things. Then, we're going to graph the original function on the graphing calculator, and there will be curves on the calculator that we will copy onto our hand-drawn graph to finish the graph up. So for the first one, we have 1 over x minus 4. So let's list all of our things that we need. The x-intercept, you set the top equal to 0. Well, setting 1 equal to 0 doesn't make any sense. So there's no x-intercept for this one. Y-intercept, you replace all of the zeros with x's. So that's going to be y equals 1 over 0 minus 4, which is negative 1/4. So let's put the y-intercept on, maybe about right there. The vertical asymptotes, we set the bottom equal to 0, x minus 4 equals 0. Horizontal asymptote is at x equals 4. So 1, 2, 3, 4, that would be right here. Oh, I wanted that to be red. And horizontal asymptote, I'm struggling with the pen thickness here. Horizontal asymptote, degree of the top would be 0 because there's no variable at all. Degree of the bottom would be 1. Top is less than the bottom. That means the horizontal asymptote is y equals 0, which is the x-axis. Now, that's not the graph itself. Those are just guidelines to help us draw the graph. To finish it up, we're going to put the original function into the calculator and copy those curves onto our graph. They're going to get close to the asymptotes but not touch them. And I want to make sure it passes through my y-intercept that I drew. And there's the complete graph. So it's quite involved. There are a lot of steps. So into the y equals, you're going to push y equals. The original function is 1 over x minus 4. When you have more than one term in the top or the bottom of a fraction, you have to have it in parentheses in your calculator, or it's not going to come out right. So seal up the bottom in a parentheses, 1 divided by parentheses x minus 4, and close. And then the standard window, or Zoom 6, will draw the graph for you. And you can see here how the curves go. You can imagine where the vertical and horizontal asymptotes are that we already drew. Just as a side note, if you have a really old graphing calculator, especially the TI-83, sometimes it draws the vertical asymptote on the screen. And it looks kind of confusing. You can't really tell where the curves are as easily, so I think that's why they quit doing that. But if you have an older calculator, that's what's happened. So where those curves are, we're going to go back to our f of x equals 3x over x minus 3. The x-intercept, you set the top equal to 0, 3x equals 0, and divide, x is 0. So the x-intercept is 0 there. The y-intercept, you replace all of the x's with zeros. So y equals 3 times 0 over 0 minus 3, which is also 0. So the x-intercept and the y-intercept are both at 0. Vertical asymptote, set the bottom equal to 0. So the vertical is at x equals 3. Horizontal, we have to follow the rules. Degree of the top is 1. Degree of the bottom is also 1. So when the top equals the bottom, the horizontal asymptote is y equals leading coefficient over leading coefficient. 3 over 1, or just 3. So at y equals 3 is our vertical, or rather horizontal. Now we need to go to our graphing calculator to get the rest of it and copy those curves. They should get closer and closer to the asymptotes without actually hitting them. So that's the complete graph for that function. And then let's do one more. Into the y equals, if you want to put parentheses around the top, you can do that as well, but for sure around the bottom. And just zoom standard window for that. So there's how the curves look. You can see it passing through 0, 0. You can kind of tell where our vertical and horizontal asymptotes are. Go back to g of x equals negative 2 over x squared minus 9. X-intercept, set the top equal to 0. Negative 2 equals 0 makes no sense, so there's none. Y-intercept, we're going to replace all of the x's with 0. Y equals negative 2 over 0 squared minus 9, which would be negative 2 over negative 9. Negative divided by negative is a positive, 2/9. So that's barely up off onto the y-axis, 2/9. Just going to put it right there. Then the vertical asymptote, set the bottom equal to 0. It's squared, so I'm going to need to factor that. It's a difference of squares, x plus 3, x minus 3. So the vertical asymptote, setting those both equal to 0, x plus 3 equals 0, x minus 3 equals 0. So x is negative 3 and x is positive 3. So we have two of them. One at negative 3, one at positive 3. And finally, the horizontal asymptotes go back to the unfactored form. Degree of the top is 0. Degree of the bottom is 2. When the top is less than the bottom, the horizontal asymptote is y equals 0, which is the x-axis. Now to the graphing calculator. We have a curve in the middle, and then one down at the bottom right and at the bottom left. And there's our final graph. Into the y equals, we put negative 2 divided by parentheses x squared minus 9. And you can see the graph. This one has 3 curves, and make sure you make it pass through that y-intercept. So going back to our hand